in 3D. Next. And these are the different things that we'll be looking at. Lines in 2D, lines in 3D, vector equation, parametric equation, symmetric equation, equation of a line segment, intersecting lines and parallel lines, angles between two lines, and lines intersecting the coordinate plane. So I now hand you over to Sir Alex, who will be discussing lines in 2D.
Thank you, Miss. So in starting off with a review of lines in 2D, just give me 1 second. So it says a line in 2D lies on the XY plane and is described using two coordinates, X and Y. From since high school, I can remember whenever we plot lines on a graph or points on a graph, I should say, this is what we would make use of our Cartesian plane, and we would use coordinates in terms of X and Y. A line can be determined by one, a point on the line, which is P naught, with the coordinates X naught and Y naught, and two, a direction vector, um, vector
Just
V.
1 second, Alex. If you can annotate on the part of the
Yes, sir.
slide that you're at, would be nice, right? At least we'll know where you are and what you're talking about, right?
Yes, sir. Yes, so one, a point on the line P naught, with the coordinates X naught and Y naught, and two, a direction vector, vector V is equal to A comma B. Right, I'm having some issues with this. Yeah. So the equation or the vector equation is given as vector R is equal to vector R naught plus a parameter T times vector V. And in coordinate form, it can be written as xy is equal to x naught comma y naught plus t times in bracket a comma b. So basically, you're using back the coordinates from the point along with the vector. In this case, it would be a, and then it would be y, and then you would have b. Where t is a parameter. T basically tells you where you are on the line. And if you change the value of t, you would basically move along the line. And the parametric equation is given as x is equal to x naught plus at, comma, and y is equal to y naught plus bt, or b times t. So let's look at an example. So this example says, find the vector and parametric equations of the line through the point 1, 2 with direction vector 3, 1. So in this case, we're given the point P naught, and its coordinates are 1, 2, and vector V is equal to 3, 1, or our direction vector is 3, 1. So we simply substitute back into the previous given equation of vector r is equal to vector r naught plus t times vector v. And when we substitute that, the first part becomes 1, comma 2 in the first bracket, plus our t parameter times in the second bracket, 3, comma 1. In coordinate form, we do something similar where the first bracket would be 1, comma 2 plus t in bracket 3, comma 1. So our parametric equations become first, we would have x is equal to 1 plus 3t, which is basically the first coordinate or the x coordinate, which is 1, plus the first part of our direction vector. And then we include the given t parameter. And y is equal to 2, which is our y coordinate, plus t. Well, t in this case, t is given, and the vector, the direction vector would be 1. And 1 times t would basically give you back t. So it becomes y is equal to 2 plus t. So if we were to represent this on a graph, this is what it would basically look like because it's two-dimensional. You would have your, let's annotate. Yeah, you would have your point 1, 2 as given by the question. So we have our point there represented by the labeling PO. And then if we move along using our direction vector, which is 3, 1, we would end up at this point here, 4, 3, which is represented by P1. So this is what our line would look like with our direction. All right, and I now hand you over to Miss Rebecca to continue with lines in 3D.
Okay, so now before we move on, we want to know what is the definition of lines in 3D. Now think of lines in 3D as a straight laser beam shooting through space where you need one point it hits and which way it's pointing. So that is how you think of a line in 3D. And here we have a definition. In 3D geometry, a line is an infinite set of points extending in both directions in space. It is determined by a point PO that is X, O, Y, O, and Z, O. It passes through and a direction vector ABC, which gives its orientation in space. Now, lines in 3D have 3 axes. We have the x-axis, y-axis, and the z-axis. Now, what the definition is really saying here, we have the point PO, which is the starting point, consists of x0, y0, and z0. And then we have the point here, P. This point P can be on any part of the line, and the line name here is L. This line here is a line in 3D, right? So from this line going upwards, this is called the vector RO. It's from the origin to the point PO. And then we have the vector R, which is from the origin to any point on the line. In this case, it's the line P. And the vector V is showing you the direction or the way in which the line moves in a direction. Next, please. And the next thing that we're going to look at is the vector equation. Now we want to derive the vector equation where in this case here we see that a necessary and sufficient condition for the point P to be on the line L is that vector POP is parallel to vector V. And we can see that from the diagram here. This line here and vector V line is parallel. So what we're going to do is, this means that there exists a scalar T. I saw talk about T in the previous slides. So we have here vector POP is equal to the scalar T times vector V. Now, to get our equation, we have let vector RO be the position vector of PO and vector R be the position vector of P. So here is where we get RO and vector R. So what we're going to do here now, we have vector R here minus vector RO is equal to the scalar T times vector V, which is equal to the POP, vector POP. And we rearrange it to make vector R the subject. And here we have the equation, vector R is equal to vector R0 plus the scalar T times vector V. So this is the equation that we will use for the vector equation. Now the equation is known as the vector equation of the line L, and the scalar T used in the equation is called a parameter. So the parameter T can be any real number. As it varies, the point P moves along the line. Now when T is equal to 0, P is the same as PO. And when T is more than 0, P is away from PO in the direction of vector V. And when T is less than 0, P is away from PO in the direction opposite V. The larger T is in absolute value, the farther away P is from PO. Now this here, we will demonstrate it more in the example. So next, please. So the next thing that we have here is the parametric equation. Now, if we switch to coordinates, the vector equation becomes xyz is equal to xoyo plus t multiply a, b, and c. So we know from here to here, they are going to be equal. Xo plus at, and then we have the next point yo plus bt, and then we have zo plus ct. So these here will be the 3 points when you are forming the equation. So two vectors are equal when their corresponding coordinates are equal. Thus, we obtain x is equal to xo plus at, y is equal to yo plus bt, and z is equal to zo plus ct. So this is the equation of the parametric equation. This is what we are going to use, where you substitute x, y, and z values. Next, please. And now we are at symmetric equations. So from the parametric equations, we know that x is equal to xo plus at, y is equal to yo plus bt, and z is equal to zo plus ct. Now, using the symmetric equations or deriving it, we solve for each one from the parametric equation for t, like we make t the subject of the formula then. So for the first one, we have t is equal to x minus xo over a. The second one, t is equal to y minus yo over b. And t the third one, t is equal to z minus 0 over c. So therefore we have x minus xo over a is equal to y minus yo over b equal to z minus 0 divided by c. So this here is our symmetric equation. Next. So example 1, we have given a point and a direction vector. Find the parametric and symmetric equations of the line through P, -1, 4, and 2 in the direction of vector V equal 1, 2, and 3. So all we do here is we substitute our whatever is given into the equation. So we're given that x0 is equal to -1, y0 is equal to 4, z0 is equal to 2. And the direction vector is a is equal to 1, b is equal to 2, and c is equal to 3. Now using our equation, we substitute our values. xo is -1, so -1 comes here. A is 1, so it remains as t. Y0 is 4, and b is 2. So that's how we have our 2t here. And z is equal to 2, and c is equal to 3. So our equation is 2 plus 3t. And this here is our parametric equation. So the symmetric equations now will be where we make t the subject of the formula. And that is how we get x plus 1 over 1 is equal to y minus 4 over 2 is equal to z minus 2 over 3. So for all three of this, we made t the subject of the formula from the parametric equation. And by put in the equation, the parametric equation into Desmos, this is what the 3D graph would look like with the line. So the first thing we have is we have to identify our axis, x, y, and z axis. So now based on the equation that we come up with, where we have x equal -1 plus t, y equal 4 plus 2t, z equal 2 plus 3t, these are the different points we can have on the line. So how to read this here? We have here, the red line represents all the points, what I just called out here. And t controls movement along the line. So whatever t is, what the value of t is going to change on the line. So if t is equal to 0, that is our starting point here. So it's going to remain as -1, 4, and 2. Now, if t is more than 0, it moves in the direction of the vector 1, 2, 3. And in this case, we use t as it's equal to 1. So that means the point is going to be 0, 6, and 5. And that is how our point is here. And if we use t as -1, the point become -2, 2, and -1. Again, this is where we insert or we substitute -1 into this equation here. And that is how we get the value -2, 2, and -1. And the same thing you do for if t is equal to 0, you substitute here, and this here will be our points. So again, we are dealing with 3 sets of points since it's a 3D graph. Next. Now, as t increases, you could go back. As t increases, you move from the point C to A, and then you move to B. So, and if it decreases, you're moving down from B to A and then A to C. Yes, so that's it for the force example. Next. The second example deals with line through 2 points. So we have here, find the parametric equations of the line P1, which is 1, 2, and 3, and P2, which is 2, 4, and 1. So when we are given 2 points in this case here, we have to find the direction vector. And in order to find the direction vector, we have here vector P1, P2 is equal to x2 minus x1, y2 minus y1, and z2 minus z1. So over here is going to be all the 2's, and over here is going to be all the 1's. So we just do normal subtraction where we have 2 minus 1 give us 1, 4 minus 2 give us 2, and 1 minus 3 give us negative 2. So this becomes our direction vector. So now we can use P1 is equal to 1, 2, 3. We have the formula here, the equation. X is equal to x0 plus et, y is equal to y0 plus bt, and z is equal to z0 plus ct. We substitute our values now. In the force equation, x is equal to 1 plus t. So that's how we have here, because we have 1 here, and then we have the direction vector as 1, and that remains t. And y is equal to 2, and the direction vector we have 2, so we have 2 plus 2t. And z is equal to 3 minus 2t. And again, we can plug this into Desmos, and we have our graph. Good. So when you put in those equations into Desmos, you could see the 3D space here with the 3D line. Again, the axes are x, y, and z. So we can see our axes x, y, and z. Good. Now, what we have are the points are the 3 different equations. Now, the green line here represents all the points that we just come up with. And again, t controls the movement along the line where you substitute. If t is equal to 0, it will be the starting point, which is 1, 2, and 3. And if t is equal to 1, we have our points are 2, 4, and 1. If we have t is equal to -1, which is less than 0, then the points will be 0, 0, and 5. Now, each point on the green line corresponds to a value of t. So if we are increasing, you move towards B, because that is moving to a positive side. And if you're decreasing, you move towards C. And that is it for the parametric equations. I now hand you over to Sir Alex.
Thank you, Miss. Next, we move on to the equation of a line segment. So as the last example that Miss was illustrating to us, we can find the equation of a line if we are given 2 points instead of just a point and a direction vector. So suppose that we are given 2 points on a line, and just update. So we're given P naught is equal to the coordinates x naught, y naught, and z naught, and P1 is given as x1, y1, and z1. Then the direction of P naught P1 would be equal to this here, which Miss would have shown us previously. X1 minus X naught, Y1 minus Y naught, and Z1 minus Z naught. And this is the direction vector for the line. So in using P naught for the point and using the direction vector of P naught P1, we see that the parametric equations of the line are. So in using these two pieces of information as our criteria, we would now have these parametric equations, which is basically the x component, the y component, and the z component, plus our parameter t, and the different, in bracket, the different points that we would subtract, x1 minus x naught. However, this can usually be written in a different way, simply by if we distribute t, meaning if we come back here, if we multiply by t throughout, and then we group the like terms and we factor out the x naught, we would end up with, instead of x naught plus t in bracket x1 minus x naught, we would now have 1 minus t in bracket, and we would have x naught plus xt, tx1. And we basically do the same thing where we factor out x naught and we write what remains. So we would have, for y, we would have 1 minus t bracket y naught plus t y1, and for z, we would have 1 minus t in bracket, and then we'd have z naught plus t z1. So when t is equal to 0, we are at the point PO, and when t is equal to 1, we are at the point P1. So if t is allowed to take on any real value, then this equation will describe the whole line. On the other hand, if we restrict t to the coordinate 0, 1, then this equation describes the portion of the line between PO and P1, which is the line segment, or is basically the definition of a line segment from PO to P1. So we're restricting it to 2 points, basically. So we have an example that says, find the equation of the line segment from P naught, which is equal to 1, 2, 3, to P1, which is 2, 4, 1. So using back the equations that we were introduced to in the previous slide, which is x is equal to 1 minus t in bracket xo plus tx1, y is equal to 1 minus t in bracket yo plus ty1, and z is equal to, in bracket, 1 minus t, zo plus tz1. We simply substitute the values of xo and tx1, and that would give us x is equal to, in bracket, 1 minus t, and 1 plus 2t, y is equal to, in bracket, y minus t, times 2 plus 4t, and z is equal to, in bracket, 1 minus t times 3 plus t, with t is an element of 0, 1, or the coordinate 0, 1. So what is the relationship between two lines in 3D? So first, in 2D, two lines are usually parallel or intersecting. In 3D, however, there is another possibility, which is skew lines. So in 3D, two lines may be either parallel, intersecting, or they may be skew. So first, we're going to look at parallel lines. So it says two lines are parallel if their direction vectors are scalar multiples. That is, if V1 is equal to, let's say, A, B, C, or the direction V1 is equal to A, B, C, and vector V2 is equal to D, E, F. Then the lines are parallel if V2, or the vector V2, is equal to K times vector V1 for some constant K. So example, let's say we have the vector V1 is equal to 1, 2, 3, and we have V2 is equal to 2, 4, 6. We would say that they are parallel because basically if there is a value or a constant for K, in this case it's 2, times the values of V1, and if they give us multiples such as 2, 4, and 6, then therefore we can say that vector V2 is equal to 2 times vector V1. So it's basically like simple multiplication. If you multiply 2 by 1, it gives you 2. If you multiply 2 by 2, it gives you 4. And if you multiply 2 by 3, it gives you 6, which are the multiples that they refer into. Next, intersecting lines. So two lines intersect if they share a common point. So suppose we have the first line L1, vector R is equal to vector R naught plus T times vector V, and the second line L2, vector R is equal to vector R naught plus S times vector U. They intersect if the values of T and S such that whatever we have for vector R naught plus T times vector V is equal to vector RO plus S times vector U. So this example, I just move this out of the way. Yeah, this example was taken from the notes provided. It says, let L1 be the line through the point 1, comma, minus 6, comma 2 with direction vector 1, 2, 1, and L2 be the line through the point 0, 4, 1 with direction vector 2, 1, 2. Determine if the lines are parallel or if they intersect or if they are skew. If they intersect, find the point at which they intersect. So they're kind of telling us from the question itself that there's some form of intersection going on, but we should still test to see, if it's parallel or if it's some other form. So the first thing we would do is we would test to see if the lines are parallel based on what we did previously with the scalar multiples. So in this case, we know that the direction vector for the first line is given as 1, 2, 1, and we know that the direction vector for the second line is given as 2, 1, 2. And in this case, instead of k, the parameter is given as c. So if we are to multiply by a value c, we would have 1 is equal to 2c, 2 is equal to c, and 1 is equal to 2c. And there would be no solution in terms of finding a value for c that would give you the multiples. So in this case, these lines would not be parallel. So we would now derive, we know that it's not parallel, so we move on to test to see if it is intersecting lines. So when we derive our equations based on the previous examples, for L1, we would have x is equal to 1 plus t, y would be equal to minus 6 plus 2t, and z would be equal to 2 plus t. And for the second line, L2, x would be equal to 2s, y would be equal to 4 plus s, and z would be equal to 1 plus 2s. So the lines will intersect if we can basically solve these equations here. Basically, you take the what x is equal to for L1, and you put what it's equal to for L2. So in this case, it was 1 plus t, and this would be equal to 2s, which is what we have over here. For y, L1 was minus 6 plus 2t, and for L2, it was 4 plus s, which is what we have here. So we have to solve this one as well. And then for z, L1 was 2 plus t, and this is equal to, for L2, 1 plus 2s, which is our second equation. So if we make t the subject for equation 1, this is equal to 2s minus 1. And if we substitute that into equation 2, so we write back equation 2, minus 6 plus 2t is equal to 4 plus s. And where we see t, we simply write what t was equal to, which is 2s minus 1, which is here. We work with the brackets. That gives us minus 6 plus 4s minus 2 is equal to our right-hand side, 4 plus s. Therefore, if 3s is equal to 12, then s would be equal to 4. So we continue with the example. From equation 1, we know that t is equal to 2s minus 1. And we found s just now to be 4. So if we just do some basic substitution, we can work out that t is equal to 7. To verify this, we can replace the values that we found for x, which is 4, and we found t to be 7 just now, into equation 3. And if we substitute that into equation 3, this works out to 9 on the left-hand side is equal to 9 on the right-hand side. So this basically tells us that the two lines intersect. To now find the point of intersection, we can use the equation of either line with the value of the corresponding parameter. For example, if we use L1, the parameter is t, and the value of t gives the point of intersection t is equal to 7. Thus, the point of intersection is, we simply substitute the value, we substitute the value t is equal to 7. So x is equal to 1 plus 7, which would give us 8. Y would be equal to minus 6 plus 2 times 7 again, which is the value of t, and that works out to 8, so y is equal to 8. And z would be equal to 2 plus 7, which gives us 9. So these would be our points of intersection. So I would have mentioned skew lines a while back. So what exactly are skew lines? Skew lines are lines that are not parallel. They do not intersect. They lie in different planes. This can only happen in 3D. How to identify skew lines? We check if the direction vectors are scalar multiples. If yes, they are parallel. If not parallel, we solve the parametric equations. If there is no solution, they are skew. Next, we move on to angle between two lines. The angle between two lines is the angle between their direction vectors. If the direction vectors are vector u and vector v, then using cos theta is equal to um, vector u times vector v over the value of vector u times the value of vector v. So if we are to look at that in terms of an example, it says find the angle between the two previous lines. And the vectors given for the two previous lines are vector u, vector u is equal to 1, 2, 1, and vector v was given as 2, 1, 2. This is from the previous example. The smallest angle between these vectors is, we simply use back our equation, but in this case, we're finding for theta. So it would be the cos inverse of this here, and we substitute. So it would basically be 2 plus 2 plus 2 over the root of 6, the root of 9. So this would work out to 6 in the numerator. And if we square root, 6, that would give us 3 root 6. And if we put this into the calculator, it works out to the angle 35.26 degrees. Finally, we're going to look at the intersection with coordinate planes. So this means a line can intersect the coordinate plane. We know this from experience when we plot points on a graph. The coordinate planes are the xy plane, where z would be equal to 0, the xz plane, where y would be equal to 0, and the yz plane, where x would be equal to 0. So looking at an example, it says find the points at which L1 in the example above intersects with the coordinate planes. So the parametric equations of L1 we found to be x is equal to 1 plus t, y is equal to minus 6 plus 2t, and z is equal to 2 plus t. So this information is from the previous example. So we're going to go through the three different planes as mentioned in the previous slide. So if we start with the intersection with the xy plane, we know that z would be equal to 0. And if we replace in the equation L1, we will get t is equal to minus 2. This now lets us find x and y. So x would be equal to 1, we're using back here, 1 minus 2, which would give us minus 1. And y would be equal to minus 6 plus 2. And instead of t, we replace that with what t is equal to, which is minus 2. And that gives us negative 10. Thus, L1 intersects the xy plane at the points minus 1, minus 10, 0. For the second part, intersection with the xz plane, we know that in this case, y would be equal to 0. So if we use the same technique above, we would get 0 is equal to minus 6 plus 2t, or in this case, t works out to positive 3. Thus, if we substitute, x is equal to 1 plus 3, which gives us our first coordinate, which is 4. Z would be equal to 2 plus 3, which gives us 5. Thus, L1 intersects the xz plane at the coordinates 4, 0, because y was given as 0, 5. And on the last plane, which is intersection with the yz plane, x would be equal to 0. So using back our equations, 0 would be equal to 1 plus t, or t would be equal to minus 1. This gives us y is equal to minus 6 plus 2, in bracket minus 1. So when we work that out, it gives us minus 8. And z would be equal to 2 minus 1, which gives us positive 1. So it follows that for L1, the intersection on the yz plane would be at the coordinates 0, minus 8, 1. So that brings us to the end of the presentation on lines in 3D. Thank you.